So in our last lecture, we saw what happens when the ball reaches here. Agreed? At this point, the ball has a potential energy and a kinetic energy. Now, question is, this particular kinetic energy is actually due to the potential energy that it has lost. For example, let us do it here. Okay. So when the ball, so you can see that initially the ball was here, that the ball was at a height h. Now the ball fell here half some distance downward, and now the height is h dash. So remember, I'm always measuring the height from below. Agreed? Now at this point, if I say that the ball has attained a kinetic energy of half m v dash square. Now question is, from where did the kinetic energy come? The kinetic energy actually comes from the loss of potential energy when it falls from here to here. So can you tell me what is the change in potential energy or loss in potential energy when falling from height h to h dash? So initially it has potential energy m g h, and then it has potential energy m g h dash. So when you subtract these two potential energy, this is the exact loss of potential energy. Now this loss in potential energy actually gave rise to the kinetic energy that it has when it is at the position h dash. Agreed? Now let us try to equate them. So when we equate them, we get m into g into h, okay, minus m g h dash. So the loss in potential energy is equals to the gain in kinetic energy. What is the kinetic energy gained? It is half m v dash square. Remember, v dash is the velocity at position h dash, and this v was the final velocity, that is the velocity when the ball is very near to the ground. So the entire potential energy has got converted into kinetic energy, but here some of the potential energy has got converted into kinetic energy, not all. If we little bit do algebraic manipulation, that we find that m g h equals half m v dash square. This is the kinetic energy, and we get a mgh. So amazingly, you see an interesting thing, that the total energy is always same. See, when the ball is at the top, the total energy is mgh. Okay, when the ball is at the top, the total energy is mgh. Now when the ball is at height h dash, the total energy is kinetic energy plus the potential energy mg h dash. Okay, and what was the energy at the top? The total energy at the top was only potential energy, which is mgh. Now our equation is saying that this energy is equal to this energy. Now what is this energy? This energy is actually the total energy when the ball is at height h dash. This energy is the total energy when the ball is at the top. Now when the ball is very near to the ground, then the entire mgh will get converted into the kinetic energy. So mgh is half m v square. It means that the complete potential energy has got converted into the kinetic energy. So at this point, we have what? We have only kinetic energy, that is half into m into v square. And interestingly, you will also find that this is also equal to this. What I want to say here is that the total energy of the system, that is kinetic plus potential, is always constant. That is, the total energy means you have to add the potential energy at that point and the kinetic energy at that point, and this total energy of the system is always constant. Agreed? This was a very simple example. Let us continue with example of a spring. Okay, so continuing our example, So now consider that you have a spring mass system. Okay, now consider this was the equilibrium position where the mass makes no motion. So the mass is happily here and nothing happens to the mass. Now what you do is, now you push the mass this side by a distance x. So now you have to push your mass by how much distance? By x. So this is x equals to 0. So let me draw a straight line so that I know which is my x equals to 0. So this is my x equals to 0. Okay, and now I need to take my mass to the other side, and the spring has got compressed. The mass is here. So where is the mass now? The mass has been displaced by position x. Now this mass has the power to move along this direction. The moment I say that the mass has the capacity to move once it is left, it means the mass has stored some energy in it. That energy is your potential energy. So potential energy in a stretched or compressed spring is always half into k is the spring constant, into the amount of displacement happened, that is x square. So this is the energy that that this mass is currently that this mass is stored in it. Okay, now if I tell you leave the mass, so what happens when you leave the mass? It will go this side, and then consider that the spring is not attached. Okay, the spring is not completely attached. Then what will happen? The mass will continue moving. So once it is left, the mass will be moving in the other direction, and the mass will be somewhere here, and then the spring, the new position will be of the spring will be somewhere here. You see that the spring and the mass has got detached, and the mass will be moving at a particular velocity v. Now if you are asked what is the velocity v with which the mass will move, that's very easy. Since the entire system has got detached, then the total potential energy has got converted into the total kinetic energy. That is half kx square has got converted into half mv square. So you can easily guess the value of velocity. Okay, so value of velocity will be root over of k divided by m into x. Agreed? But now if I tell you a state in between. Okay, now if I tell you a state in between, so let us see what happens. So now instead of the mass getting completely detached, now for example, so what happened initially? The mass was at x equals to 0. Then you took the mass and compressed it till x. Now imagine that the mass is somewhere around here at x. Okay, now if somebody asks you what is the energy of the object, okay, so at this position the mass has only potential energy because it was not moving at all. So at this position the energy was half into k into x square. Agreed? There was no kinetic energy as there was no motion. But at this position x, the object has some velocity. It means it has not only a particular potential energy, but it has also some kinetic energy. Now assume that at this position the mass has velocity v dash. Okay, then can you tell me what is the kinetic energy? Obviously kinetic energy is very easy. You will write it as half m v dash square. Now you will be asked what is the potential energy. Obviously, you see at this point, what is the value of the stretching position? It is x dex. So from equilibrium, the mass or the spring has been stretched by a distance x dex. So potential energy is half k x dash square. So here we have both kinetic and potential energy because the spring and the mass has not completely got detached. This position is, so when you go from position A when the spring was completely attached um, to position B when the spring was completely detached, then let me write it as C. When the spring was completely detached, in between there was a position B when the spring was neither completely attached nor completely detached. This is the position B, where it has both kinetic and potential energy. So you see, in case 1, the mass has only potential energy because it was completely compressed. In case 2, when the mass got out of the spring clutches, it has only the kinetic energy. And in case 3, when the spring and mass were not completely detached, it had both kinetic and potential energy. And let me tell you one thing, the conservation of energy says that all these energies are same. The total energy is always same. So what is the total energy in case 1? In case 1, the total energy was only the potential energy, that is half k x dex square. Then in between, where it was neither completely detached nor completely attached, so in between it has, so this is x. Okay. Now in between it has both potential energy, so half k x dex square, and it has both kinetic energy. Then what happens? Then the mass crosses the equilibrium position and then gets completely detached from the spring, like it happened here. So when the mass gets completely detached from the spring, then there is only one energy, that is your kinetic energy, because the spring is no more in action. So what is the velocity, total energy? The total energy is half mv square. So the law says, conservation of energy says that your total energy, that is the potential plus kinetic. Now you'll say, why there is no kinetic energy here? Because the kinetic energy is zero. That's why the complete energy, this is not only potential energy, this is complete energy, because when the object was here there was no kinetic energy, so you don't see another term. Then in the second state it has both kinetic and potential, and in the third state it has both kinetic and potential, but at this state the potential is actually zero because there is no spring attached. So here also we have considered the total energy. Agreed? So total energy of a system is always constant, is always constant. So remember that. Okay. So this is law of conservation of energy. So we learned something interesting about the fact that there is something called as the total energy of the system, and total energy of the system is always constant. It never changes until unless there is some friction or loss of energy. So we are not concerned with the loss of energy. We are just concerned with an ideal condition where the total energy is always constant. So this energy thing is a very interesting way to solve problems. Okay. Why I said you very interesting to solve problems? Because you see, if you can look at this equation quickly, then you see by using energy conservation law, I was able to predict the final velocity of the mass. Quite amazing, right? I didn't use any force equation, I didn't do any integration or differentiation. I just used the energy concept and I was happily able to find what will be the velocity of the mass when it has got completely detached from the spring. Very happily I was able to find it just by using energy. Similarly, when in this case 1, so when I was teaching about there was a ground and there was a ball and the ball is falling down. Okay, I calculated what will be the velocity of the ball exactly at this position when the object is very near to the ground by using energy conservation. How I calculated it? I just said that the total energy of the system is mgh here, and the total energy of the system is half mv square here, because when the ball goes down the total energy has got converted into kinetic energy. and then I equated these two equation, and happily I found that the velocity is root over of 2gh. So don't you find it amazing that instead of using any force equation or any integration differentiation, I'm easily able to solve some problems just by using the conservation of energy law. Okay, so there are many complicated problems in physics that can be solved just by using the conservation of energy. Agreed? One such example, let me give you. Okay, consider one more example to clear your mind. So let me rub all this. Okay. Do you remember the pulley system that we studied in our basic uh, classical mechanics? What happened in the pulley system? You have a pulley, and both side you have masses attached to the pulley. Agreed? And you are studying this particular system. So there is mass 1 and there is a mass 2. And remember how we solved this system? So this is of mass say m1, and this is mass m2. Agreed? And we solved this system by using forces. Remember, we solved this system by using forces. We talked about tension, we talked about mg, we talked about ma. So just go to the basic pulley problems that we have solved in our basic classical mechanics. These were the things we talked about. Now question is, so what were the solution? Let me write the solution. So if m2 is greater than m1, then we learned that m2 will fall with an acceleration a and m1 will go up with an acceleration a. And by using these force equations, Newton's laws, we were able to calculate the tension and we were able to calculate the acceleration. Agreed? So go to the previous section and find it how we calculated. Now question is, can we solve this pulley problem by using the conservation of energy method? The answer is yes, we can actually solve this pulley problem by using conservation of energy. That we'll do in our next class.